All right, so far we've talked about how lines can be perpendicular, which means they do intersect at a 90-degree angle, at a right angle. We've looked at how right angles can be split into two to form complementary angles. Now what we want to talk about is our right angle becoming involved with this idea of the shortest distance between a point and a line, and that's called perpendicularity. So if I had a line and a point someplace off of our line, we'll call it point A, and down here we'll call this point B, or line BC. If I want the shortest distance between point A and my line BC, it would go straight down and immediately form this right angle. Let's go ahead now and name that point D. So the shortest distance from A to our line BC is going to be this distance because of the right angle. Now you might be wondering, well, what would make it different? If I took A and brought it out to C, there is a distance between A and C. If I brought it out to B, there is a distance between A and B. But clearly, even if we look at this, doesn't that look like the hypotenuse of a right triangle? And we know in our right triangle the hypotenuse is longer than the legs of our right triangle. So already we can tell that the distance from A to D has to be shorter than either of these. Why? Because of the right angle. So when we talk about perpendicularity, we're talking about the distance from any point to a line, but it has to be a right angle. Now, where might this actually come into play besides naming the segment? Again, this segment would be the shortest segment to all of these. And again, keep in mind, these do look like right triangles. They are right triangles. These are longer. So what we're going to do is we're going to look at this again, but we're going to look at it where they want us to apply some of our algebra knowledge. So here's an example. Looks very much the same. And we have our point A again up top. They're showing us that that's a right angle, so we know that that's going to be the shortest distance to our line BC. But this time we're going to label the distance x plus 7. Of course, we're going to bring in algebra. And then we're going to label this distance 21. Now don't get confused, we're not doing the Pythagorean theorem. We just want to solve for x with this particular situation. And again, because this is the shortest distance, I don't care what this actually measures, even though we know this actually measures 21. We want to know what could this be if this is in fact the shortest distance. So when we talk about perpendicularity, we are going to look at what's called an inequality. We know this is the shortest distance from A to the line. This guy has to be bigger. So what we're going to do is we're going to write an inequality that states, let's make this D now, that AD has to be less than AC. Again, shortest distance, so it has to be smaller than AC. Instead of leaving it like this, just like we've done all along with our segment addition postulate, substitute in the values. This says the length of AD, this says the length of AC. So the length of AD is x plus 7 less than 21. If I want to figure out what the values of x could be, just subtract 7. And we find out that x has to be less than 14. So all we did here was use the idea that this is the shortest segment because it's the shortest distance from our point to our line. We created a logical inequality that says AD is shorter than AC. We plugged in the values to figure out what are the possible values for x. Now think about what it says here. It says x has to be smaller than 14. If I plugged 14 in here, 14 plus 7 is 21. We know that they're not equal, but we know this one's supposed to be less. So if I plugged in 13, 20 is less than 21. If I plugged in 12, 19 is less than 21. And I could keep going. In fact, I can go as low as, if I plugged in 0, x could be 0, because if I added it to 7, legitimately it would still be a length of 7, which is less than 21. If I plugged in even a negative number, Negative 1 plus 7 is 6. Negative 2 plus 7 is 5. Negative 3 plus 7 is 4. And I could keep going because all of them are less than 21 and it fits the requirement. The problem is I can't go any lower than negative 6. Because if I plugged in negative 6 plus 7, it's 1. What happens if I plugged in negative 7? I'd end up with 0. So I know that x can be less than 14, but because I don't want this to be 0, our x has to be greater than negative 7. So it has to be less than 14, but has to be greater than whatever would make this 0. So that's how we know what that is, and this is how we know what our value could be so that it does fit that this is the shortest distance compared to the other one. All right, the next example that we're going to look at with perpendicularity is this one where we have our points D, E, F, and G. Our line segment this time, so whether it's a line or a line segment, is EG, and we're looking at D being a point off of our line, and D, the shortest distance from point D to this line segment, is right here. We can see that the right angle tells us that this has to be the shortest distance. Because we know the shortest distance from a point off of a line to a line is created by this 90-degree angle, we want to look at the inequality that this is going to follow. And again, shortest distance is here. You can see that this has to be longer, again, because we do form this right triangle, so this piece has to be longer than this. This is the leg of our triangle, that's the hypotenuse. So when we create our inequality, we're going to write out that DF has to be less than DE. Again, shortest, longer. So when I have our length of DF and our length of DE, we have 2x minus 3 is less than 25. We'll go ahead and now do regular algebra. We're going to add 3 to both sides, and we end up with 2x is less than 28. And when we divide by 2, we end up with x is less than 14. So again, if I plugged in the value here, we know that if I plugged in 13, 2 times 13 is 26. 26 minus 3, that's going to work. Less than 25. 26 minus 3 is 23. That's less than 25. If I kept going, I could plug in values 12, 11, 10, 9, 8, all the way down, but what we need to think about is we don't want this to be 0. Now the last example was pretty easy to come up with what it couldn't be, because it was just in the last example x minus or x plus 7. Not a whole bunch of guessing here, but this one might not be as easy to come up with mentally. So think about it. If we don't want this to be 0, let's pretend it is 0. So take your 2x minus 3 and force it to be 0. If I add 3 to both sides, 2x equals 3. And if I divide by 2, I end up with 3 over 2, which is 1 and 1/2. And what I find out is if I don't want this to be 0, I can't plug in 1 and 1/2. I could plug in the number 2, and 2 times 2 is 4, minus 3 still gives me a length of 1. So that means I can take anything that's bigger than 1 and 1/2. This is what x has to be bigger than, but this is what x has to be smaller than in order for us to know that this is in fact the shortest distance to the line segment EG.